Hello, in this video we're going to talk about Newton's law of gravitation. The definition of it is an equation that relates the masses of bodies and the distance between their centers to the force. And so what we have here is we have the force of gravity, Fg, and we have this big M here like this, and we have another M like this. And we have this r, which we've already seen is the distance between the centers of objects. And g is a constant, like the Coulomb constant. It's the gravitational constant, and it has this value, and we should store it as the letter g in our calculator. It also has the same units, newtons, as the electrostatic force. And the formula behaves very much the same way as the electrostatic formula. Direction matters, but gravity is only attractive. It's not like electricity that is both attractive and repulsive. So we want to talk a little bit about the meaning of mass. Mass is the amount of matter in a body. So for example, if you were a person standing on the earth and you counted up the number of atoms you had, and then you went to the moon, the mass would be equal. The mass is equal, the mass of the moon is equal to the mass, your mass on the earth. Not the mass of the earth, but your mass on the moon and your mass on the earth are equal to each other. But there is something that changes, and that thing that changes is the force of gravity. And we've previously calculated the force of gravity, right? So we know our mass, let's say it's 50 kilograms. The gravitational constant on Earth is 9.80665, and we can use 10 when it's easy. So we have a force of gravity of 500 newtons. So we have 500 newtons is our force of gravity on the Earth. But when we get to the moon, the acceleration caused by gravity is only 1.6. So we would only be 80 newtons on the Earth. So what's different is the gravity is different. And that force of gravity, we would connect that to the idea of weight. We will weigh less, but really what we're detecting is the force of gravity. So we can think about this as a person standing on the Earth has the same mass as when they're standing on the moon, but their force of gravities or their weights are different. Now we can see here that on the moon it's 1.6, on the Earth it's 9.8, and on Mars it's 3.7. Now, notice the units here are newtons per kilogram. We have previously thought these units were meters per second squared. Well, it turns out these units are the same thing. Newtons per kilogram is meters per second squared. The gravitational field strength is the acceleration caused by gravity. So this g has two names. Acceleration caused by gravity, and it's the gravitational field strength. When we speak of it as having the gravitational field strength, we usually use newtons per kilogram. When it's acceleration, we use meters per second squared, but the numbers are the same. So now looking at these three locations, the moon, 1.6, you're going to be very light on the moon. You're going to be heavy on the Earth, and somewhere in between on Mars, maybe a little more than twice as heavy as you would be on the Earth, but almost a third of the weight you'd have on the Earth. Now, many people want to know about weightlessness and what that means. And the short of it is this. Weightlessness is the feeling of free fall. No normal force. So let me give you an example. When someone is in the space station, you might say there's no gravity because they're floating around. But the real reason for that is they are falling. They are in free fall. Isaac Newton had this idea, and he said if there were a mountain and you put a cannon on the top of that mountain and you fired a bullet, it would travel like this. But if you fired it faster, it would travel like this. And if you fired it even faster, it would travel like this. And if you fired it fast enough, it would go all the way around the Earth. And that's what it's like to be in orbit. You're in free fall. If you tried to stand on something, you can't because there's nothing to hold up the scale. But if you stopped this satellite for a moment, the people inside it would fall to the edge. And if you stopped the satellite and held it in place, a great big giant came and held that satellite there, grabbed it out of the sky and held it, the people in it would fall to the ground and they would stand on the scale and they would weigh about 90% of what they weigh on the Earth. The gravity is less, but it's still very close to what it is on the Earth. So the reason people appear weightlessness is that they are in free fall. All right, so what would happen in some different cases here? If we doubled the mass of an object, well, that would become 2, so the force of gravity would become 2. What if we doubled both? Well, in the numerator, 2 times 2 would be 4 times as much gravity. What if we doubled r? Well, that would be over 4, or 1/4 as large. What if we doubled m, little m, and r? Well, that would be 4 on top and 4 on bottom, or it would be the same size. What if we tripled the m, doubled the other m, and quadrupled the r? Well, that would be 6 over 16, or 3/8. It would be 3/8 as large by changing those conditions. Lastly, we can do a calculation. We do a calculation on gravity. So we've got the sun and the earth. Sun and the earth, like so. We want to calculate the force of gravity between them. Big G, big M, little m over r squared. And big G is 6.67 times 10 to the minus 11th. I put in a minus there. I was missing that minus. The big mass of the sun is 1.98 times 10 to the 30th. And the mass of the earth was 5.9772 times 10 to the 24th. Now, it's interesting, if you compare this 10 to the 30th to 10 to the 24th, that's a 10 to the 6th difference. Or in other words, the sun is 1,000,000 times more massive than the earth. And then we need the distance. Oops. Yes, this number is 10 to the 11th, sorry. Is 1.49 times 10 to the 11th meters squared. So we put that in. We use our gravitational constant times 1.98 times 10 to the 30th times 5.9772 times 10 to the 24th divided by 1.495 times 10 to the 11th squared. And we get 3.53 times 10 to the 22nd newtons. That's the force of gravity. That's how big it is. Now, if you will remember, in the previous lesson for force centripetal, we got 3.54 times 10 to the 22nd newtons. So indeed, the centripetal force is the force of gravity. What is the center pointing force causing this? It is gravity.